Welcome to my YouTube channel, students. Jai Hind. Students, always try to live in the present and not in the future. You need to think about your future, but don't live in the future. Live only in the present. So what you need to do is, do your best today. Put all the hard work, all your dedication, sincerity in the present scenario and stop bothering about your future. It will itself be secured. Right, students? So with that, let's begin today's session. Today we'll be discussing about magnetic Lorentz force. It is the force experienced by a charged particle which is in motion and is under the influence of magnetic field. Right? So in this session, we'll be discussing these topics. We'll be discussing magnetic Lorentz force, all its special cases. We'll try to define the SI unit of magnetic field, that is 1 Tesla, right? Then we will be defining the electric force that we have already discussed in the previous unit of electrostatics, but we'll discuss it today itself. So it is known as electric Lorentz force. Then we'll discuss the total Lorentz force, that is when the charged particle is under the influence of both electric field as well as magnetic field, right? So let's begin with magnetic Lorentz force, which is the force experienced by a charged particle in motion under the influence of magnetic field. Lorentz. Actually, Lorentz was the scientist who have given the mathematical expression for the force experienced by a charged particle in motion under the influence of magnetic field and electric field. Accordingly, it is known as Lorentz magnetic force or Lorentz electric force, right? So, let's consider this to be x-axis, this to be y-axis, and this to be the z-axis, like this. Let us consider this to be the origin, right? So, what we consider is, let us consider the magnetic field be directed along the y direction. Magnetic field is represented by capital letter B and it is assumed to be directed along the y direction. And this is, suppose, a charged particle plus q and moving along this direction, making an angle theta with the direction of the magnetic field, right? It is making an angle theta with the direction of the magnetic field. So theta is the angle which the velocity vector of the charged particle makes with the direction of the magnetic field, right? It is inclined. Theta can be 0, it can be 90 degree, it can be 180 degree, isn't it? Its value can lie between 0 and 90. We'll discuss all the special cases later on, right? So theta, remember students, it is the angle which the direction of motion of the charged particle, that is its velocity vector, makes with the direction of the magnetic field, right? So V is inclined to magnetic field vector at an angle theta. Now students, we all are aware of the resolution of the vector into two rectangular components, isn't it? So what we'll do is, let's try to resolve this velocity vector into two components. One component of velocity of the charged particle along the direction of the magnetic field, that would obviously be V cos theta. So this component, which is along the direction of the magnetic field, it will be V cos theta. While the other component of the velocity of the charged particle will be lying in the XZ plane, which is perpendicular to the magnetic field, right? Let it be represented along the x-axis. And this component would be V sin theta. And V sin theta is the component of velocity of the charged particle, which is perpendicular to the direction of the magnetic field. And students, remember, V sin theta being perpendicular to the direction of magnetic field is also known as the normal component of velocity of the charged particle, right? So V cos theta, V sin theta. V cos theta is the velocity component of the charged particle along the direction of the magnetic field, that is along y-axis, while V sin theta is the perpendicular component of the velocity of the charged particle which lies in the XZ plane. Here, just for convenience, I have shown it along y-axis. Actually, this V sin theta can lie anywhere in the XZ plane, must be perpendicular to the magnetic field. Right? Okay. Now, Lorentz found that this charged particle, which is under the influence of magnetic field V, experiences a magnetic force. And that magnetic force is found to be first, suppose magnetic force, it's written as Fm. It is found to be in magnitude, it is found to be directly proportional to the magnitude of the charge. The greater the charge of the body under consideration, the more is the magnetic force experienced by it. Right? Second, it is found the strength of the magnetic force experienced by the charged particle is found to be directly proportional to the strength of the magnetic field. The stronger the magnetic field in the given region, the more will be the magnetic force experienced by the charged particle. Right? And third, it is found that the magnitude of the magnetic force is directly proportional to that component of velocity of the charged particle which is perpendicular to the magnetic field. That is, it is found to be directly proportional to the normal component of velocity of the charged particle. And the normal component of the velocity of the charged particle is v sine theta, which is perpendicular to the magnetic field B vector. Right? So, it is found to be directly proportional to v sine theta. Again, I repeat, students, Lorentz found that when a charged particle is moving under the influence of magnetic field, then the force experienced by the charged particle is known as magnetic Lorentz force or simply magnetic force. Experimentally, it is found to be directly proportional to the magnitude of the charge. It is also found to be directly proportional to the strength of the magnetic field in the given region. And thirdly, it is found to be directly proportional to the normal component of velocity of the charged particle, that is v sine theta, which is that component of velocity of the charged particle which is perpendicular to the magnetic field. Right? So, combining all the three, what we get is Fm is directly proportional to q v b sine theta. Clear, students? Now we are aware, in order to eliminate this proportionality sign, we need to introduce some constant of proportionality. Let it represent by k, small letter k. Therefore, what we get is Fm is equal to small letter k qvd sine theta. Now again, it's found that if q is measured in coulomb, which is its SI unit, velocity of the charged particle is measured in meter per second, magnetic field is measured in Tesla, F is measured in Newton, then the value of K in SI is found to be unity, that is 1. So, in SI, the value of K is found to be 1. Therefore, the expression for the magnetic force and magnitude is given by Q V B sine theta. This is the formula for the magnetic Lorentz force. Q V B sine theta. Theta is the angle between the velocity vector and the magnetic field vector. Right, students? So, from this particular formula, we can easily define the SI unit of magnetic field, which is Tesla. And before that, we need to find out the direction of F only. This is the magnitude. So, in order to find out the direction of this magnetic force, we need to represent it in the vector form. Here it is sine theta. So, make use of cross product or vector product. Right? So, in vector form, this magnetic force may be written as charge, it's a scalar quantity. So, it can be written as V vector cross B vector. Now, we are already aware of the properties of cross product, isn't it? V cross B, it is the cross product or the vector product, right? V cross B will give us the product of magnitude of velocity into the product of the magnitude of the magnetic field and the sign of the angle between these two. And sign of the angle between the velocity vector and the magnetic field vector is theta. Clear, students? So, this is the representation of the magnetic Lorentz force in the vector form. Now, regarding its direction, Fm is given by the cross product of V vector and B vector. Therefore, by using the properties of the cross product, magnetic force, it must be perpendicular to velocity vector and it must also be perpendicular to the magnetic field vector. It must also be perpendicular to the magnetic field vector. This is key point. If r vector is equal to a vector cross b vector, then the direction of r vector is perpendicular to the plane containing a vector as well as b vector. This we have already done in the properties of cross product in the previous session, isn't it? So, the direction of magnetic force is perpendicular to both velocity vector as well as magnetic field vector. And students, its direction, the resultant of the cross product of two vectors, its direction is given by right hand thumb rule, isn't it? Here, the orientation of the angle would be from the rotation of the velocity vector towards the magnetic field vector. So V cross B. So it will be like this. The angle is to measure from velocity vector to magnetic field vector. So in the right hand, the fingers must curl along the rotation of vector B vector along magnetic field vector. So the thumb will point towards the direction of V cross B, which will give us the direction of magnetic force, isn't it? So it is directed towards the z axis. So this is where the magnetic force would be. So obviously it is perpendicular to both magnetic field as well as the velocity vector. Clear, students? V vector and B vector, if they are lying in the plane of the board, then magnetic force would be perpendicular to the plane of the board and in the outward direction. Clear? Okay. So the direction of magnetic force can be given by Fleming's right hand thumb rule. Clear, students? Okay. So this was the magnitude and this is regarding the direction. Now let us define the SI unit of magnetic field, which is Tesla. Let's make use of this expression. Now look, B would be equal to magnetic force divided by QV sin theta. Let's make use of it, right? We are trying to define definition of 1 Tesla by using this expression. So how to get B equals to 1 Tesla? What we consider is, if charge under consideration is 1 coulomb, it is moving with unit velocity. In SI it will be meter per second. And in order to eliminate sin theta, we will consider theta to be 90 degrees, so that sin 90 becomes 1. And suppose theta is equal to 90 degree. And magnetic force experienced by this charge is suppose 1 Newton. Then substituting all these values over here, what we get? B would be equal to 1 Tesla. Is it clear, students? So now using this concept, we can easily theoretically define the SI unit of magnetic field, that is 1 Tesla. So students, please listen to me very carefully. The strength of the magnetic field in a region is said to be 1 Tesla if a charge of 1 coulomb moving with unit velocity enters the field at right angle and it experiences a force of 1 Newton. It is then the strength of the magnetic field will be said to be 1 Tesla. I'll repeat, student. The SI unit of magnetic field is Tesla. The strength of the magnetic field in a given region is said to be 1 Tesla only if a charge of 1 coulomb moving with unit velocity, that is moving with velocity of 1 meter per second, enters the magnetic field at right angle and experiences a force of 1 Newton. In that case, the strength of the magnetic field in a given region is said to be 1 Tesla. So this is how the SI unit of magnetic field is defined, right? I hope you have understood the definition, isn't it? Just remember this mathematical expression and you can define Tesla in your own words. So students, we have done the expression for the magnetic Lorentz force. We have done the definition of 1 Tesla, isn't it? Now let's concentrate on the special cases then. Okay, what we'll do is we'll consider various cases where theta is 0 degree, theta is 180 degree and so on. So let's find out the force experienced by this charged particle under various cases or under various conditions. So what we consider is, suppose Case 1. If V is equal to 0, that is, charged particle under consideration is at rest. So charged particle is not moving, it is at rest. Now what is the formula? F is equal to Q V B sin theta. Now if V equals to 0, then magnetic force would also be 0. So what it means is that a charged particle at rest will not experience any magnetic force. So students, be very clear about it. For a charged particle to experience magnetic force, it must be in motion. If the charged particle is at rest, it won't experience any magnetic force. Right? So this is case 1. Let's consider case 2. If theta is equal to 0 degree or theta is equal to 180 degree. Right, students? In this case, we are assuming the charged particle to be either moving along the direction of the magnetic field or in a direction opposite to that of the magnetic field. So the case would be somewhat like this. This is the magnetic field and this is the charged particle. So here theta would be equal to 0 degree. Or it can be like this. This is the direction of the magnetic field and the charged particle is moving in a direction opposite to that of the magnetic field. So here theta would be equal to 180 degree. Students, you are aware, sine 0 is 0, sine 180 degree is also 0. So what we get is, over here if you substitute the value of theta as 0 or 180 degree, what do you get? In both the cases, F would be equal to Q VB sine 0 or Q VB sine 180 degree. So in both the cases, we will get 0. So what we conclude is, even if the charged particle is in motion, but if it is moving either along the direction of the magnetic field or in a direction opposite to that of the magnetic field, then in that case also it won't experience any magnetic force. Right? So what do you conclude from these two cases, students? A very, very important conclusion. For a charged particle to experience magnetic Lorentz force, first point, the charged particle should be in motion, no doubt regarding that. And second essential point is that it should move in a direction other than, I repeat, it should move in a direction other than along the direction of the magnetic field or opposite to the direction of the magnetic field. In simple language, it should move in any direction other than theta equals to 0 degree or theta equals to 180 degree. Clear, students? I hope I have convinced you. Okay, let's consider case 3. Case 3, students, suppose the charged particle is moving at right angle to the direction of the magnetic field. Suppose this is the direction of the magnetic field and the charged particle is moving along this direction. The angle is 90 degree. Obviously, theta being 90 degree, sine 90 would be one which is maximum. So in this case, theta is 90 degree. Therefore, magnetic force would be maximum and it would be equal to QVB. It is QVB sine 90. Now sine 90 is 1. So the maximum magnetic force which a charged particle can experience under the influence of magnetic field is QVB. This is the expression for the maximum magnetic force experienced by the charged particle. And it will experience maximum magnetic force only when it travels in a direction perpendicular to the direction of the magnetic field. Right? So, these are the various cases. There is another very, very important point which I would like to discuss with you. That important point is the work done, I repeat, the work done by the magnetic Lorentz force is always zero. This is a very, very important property which will try to mathematically establish this fact, right? So what I've stated is, this is a very, very important point. Work done by magnetic Lorentz force is always zero. This is a very, very important point. Let's try to verify it, right? Now, just now we have discussed magnetic force. We are aware in vector form it is given by Q, V vector cross B vector. Am I clear, students? By using the properties of the vector or the cross product, what we can safely conclude that Fm vector is perpendicular to both velocity vector as well as it is perpendicular to magnetic field vector. This is the velocity vector. And also, students, we are aware velocity, it's given by time rate change in the displacement, isn't it? It is given by the time rate change in the displacement. So what I mean to say is that velocity vector must be parallel to the displacement vector. That is, the direction of the motion of the particle will be along the direction of its displacement, but obvious. So, from these two, what do you conclude from these two? So, from these two, we conclude that Fm vector is perpendicular to displacement vector. Clear, student? Magnetic force is always perpendicular to the direction of motion of the charged particle. Now, we are aware, work done, it's given by the scalar product of force and displacement. This is the scalar product or the dot product. So, work done may also be written as product of magnitude of F and displacement and cosine of the angle between them. Since these two are perpendicular to each other, the angle between them would be 90 degree or pi by 2 radians. Cos 90 is 0, therefore work done is 0. So students, to remember this very, very important result, work done by the magnetic Lorentz force is always 0. Clear? So this is a very, very important result which you need to remember always, right? Okay, now let's discuss electric Lorentz force. This we have already done in the chapter electrostatics. Electric Lorentz force. Now when a charged particle is under the influence of electric field, then obviously it tends to experience an electric force, and that electric force may be termed as electric Lorentz force, right? And we are aware the electric force is given by Q into E. E is the electric field due to a source charge, isn't it? Now, as we are aware, students, it is independent of the velocity of the charged particle. So, in order for a charge to experience electric force, the charged particle may be in motion or it may be at rest. What I mean to say is that there is a very, very basic fundamental difference between the electric force and the magnetic force. For experiencing electric force, the charged particle may be at rest or it may be in motion. While on the other hand, in order to experience magnetic force, it is mandatory for the charged particle to be in motion. Right? So, Fe is equal to QE. This is the force experienced by a charged particle under the influence of electric field. Right? Put this as A. Clear, students? Now, just now we have discussed, if the charged particle is in motion and is under the influence of magnetic field and is moving in any direction other than along or opposite to the direction of the magnetic field, then the charged particle tends to experience magnetic Lorentz force. So, magnetic Lorentz force is given by magnetic Lorentz force. It is given by
Fm vector is equal to q v vector cross b vector. Put this as b.
Now imagine a charged particle under the influence of both electric field as well as magnetic field. Then the net force experienced by the charged particle in such a case is known as total Lorentz force. So in that case, the total or net Lorentz force is given by F net in the vector form. It would be equal to electric force plus magnetic force. So let's substitute the value. So we get q E vector plus q V vector cross B vector. So students, in the vector form, the expression for the net Lorentz force would be F net equals to q bracket E vector plus V vector cross B vector. Remember, this is the cross product or the vector product. So this is the expression for the net Lorentz force experienced by the charged particle when it is under the influence of both electric field as well as magnetic field. Right, students? So we are over with all the topics in today's session, right? So I hope you have enjoyed this session while studying these new concepts. So that's it for this particular session. Do join me in my next lecture. Till then, do take very good care of yourself and always remain blessed. Thank you.